Hi, I'm going to talk for a few minutes about very simple HPC tricks. This is primarily for the novice HPC enthusiasts. And while there are a lot of material for optimizing your programs for OpenMP, MPI, Cuda, etc., there are some very simple tricks which sometimes we miss out. These are not really code-specific tricks. These are more like how you want to set up your environment, etc. Right? So that is what I am going to talk about in this short video. Right? A summary of these simple tricks related to optimizations is given in this slide. So I have divided these into different parts. Some things related to the compiler flags, how you set up various optimization levels. Some things related to PBS, which is the one that we use in our cluster. Some things, some optimization, some tricks related to the environment. And then, of course, there are things which are specific to OpenMP, MPI, and Cuda. So let's start with the first one. Often it so happens that we compile our programs, let's say Fortran or C programs using a compiler, let's say G Fortran or GCC. And there are optimizations that we do inside the code, but there are some optimizations which the compiler can do on its own. And that can be specified on the command line. Just to give you a very simple example, I'm going to show you a program which is, so let's say that I have some file jacobi.c, right? And if I compile it with gcc jacobi.c, I'm going to get a.out, which I run with some input parameter 512, which specifies the size of the problem, right? And I see that when I compile and run it, it required 4133 iterations. That is the internals of the code, and the error processing that it did, the error that it reached was in the order of 10 to the power minus 5. Importantly, it took 3.4 seconds, right? If I run it again, it will probably take around the same amount of time. And that shows how usually we compile and run the programs. The time command just tells you this particular output. There are other ways in which you should time the output. For example, there are certain parts of the code which you want to time. You should use a clock function or get time of day, etc. But here I am just showing very crude way of checking the overall time. Now what I'm going to do is to use the same command, except that I'm going to add some optimization flag, right? To tell GCC that boss, don't just compile it as it is, try to do some more work and try to optimize the program. And then I'm going to again run exactly the same command. And you can see that the total amount of time has considerably reduced. Note that the output hasn't changed. The number of iterations as well as the error, those are the same. So that's a good sign. And still the time has reduced. So this simple processing, and you can try with O1, O2, O3 and see if you get any benefit. Again, these are not hard and fast rules. I mean, it's not guaranteed that you'll get 50% improvement in your execution time. It differs across programs. It's just that what I'm trying to say is that you should definitely try these out, and whatever works suits best for your environment, you should try that. Sometimes we have this double precision or single precision in our programs. Most of the times, many of our scientific codes need to use double precision, but at times single precision is sufficient. And that can be nicely provided by using some options to the compiler. For example, for GCC, you can use -fast-math as an option, which will consider some of the constants as of 4 bytes, that is float, rather than 8 bytes, which is the double. And that can significantly improve the number of iterations that it uses to reach the fixed point, because now the width of the decimal is going to be reduced. Then there are certain pragmas which the compiler provides. For example, inside your code, you can add this hash pragma gcc unroll 4 just before a for loop, It will try to unroll the program. Unroll meaning it will make 4 total copies of the program, and that might help it perform more optimizations. Sometimes it can work in a negative manner also. But again, just I mean, this one adding one line doesn't create any problem inside the your code, especially just before a for loop. So you could just try changing even that value 4 to let's say 8 or 2 and see if that works out. All these optimizations inside the code should be targeted to the for loops which are the most time consuming. Okay, let's move on to the next part. PBS is our system which we use for submitting jobs, etc. If you are using it for OpenMP, that is for a single node, you are interested in a single node, you are interested in shared memory parallelism, then you should do a select :1. I often see that many of the scripts, they are written first for MPI and then those get migrated for OpenMP. And many times students are fully not aware of different options or the meaning of different options. So that copy paste triggers that select whatever 2 or 3 that continues with for the OpenMP program also. But that is not always a good thing to do, because as soon as there are multiple nodes, there is communication that can happen across nodes. If it is a single node, then across shared memory, it is going to be faster. So just keep that in mind. If you are doing shared memory programming, then you should in PBS you should set select :1 in your PBS script. On our Aqua cluster, while there are only 40 cores which are available, there are 80 virtual cores which are available, right? So what that means is that if I try to find out the number of cores which are specified, these are the virtual cores, virtual hosts or virtual processors. So you can see that 0 to 79 number of processors are available, which means that you can specify, again, this you should try out. You can specify NCPUs :80 instead of NCPUs :32 or 40, which you might consider as the max on a particular node. You can try changing this to 80, and if your program is such that it does not have too much of synchronization, etc., it has good parallelism, then this might get benefited. Instead of using 2 nodes having 40 cores each, you might want to use a single node having 80, let's say, processors or NCPUs, and that might improve the execution time. For MPI, again, experiment with different options. One of the options which is less known is place. Right? So by default, place equal to places value is free, which means that your process might migrate anywhere, might be distributed anywhere in the cluster in amongst the nodes that get chosen. But you might want to pack them together, or you might want to scatter them depending upon how the communication across different processes in your algorithm is. And that can lead to different options that you can give using this place option. Many of these are given in the PBS tutorial, which I have linked at the bottom of this these slides. So just to give you that, for example, this link here, that link is for the PBS training that we had conducted at IIT Madras. So both the PDF as well as the video corresponding to that are available. So request you to go through that. Many times it so happens that the waiting time in the queue is large, and sometimes you would have already submitted a job. And then you realize that maybe I want to make some small change in the job. And the default way to do it is that you do a qdel to delete that job, and then you do a q sub again to submit a new job by making this change. But there is a way to dynamically change the resource configuration of a job, and that command is called as qalter. Right? So for example, I have given an example here where there is a job which is 93939, which I have already started with 2 cores, but I want to change it to 4. So can I do a qalter there? I can, and ncpu is equal to 4, I can specify to q alter, and that will given the job id, and that will make changes to the job. There are quirks with respect to all of these. You should be aware. You should read out a little more, but it might suffice for your purpose so that you don't have to again get into the end of the queue and so on. Okay. There are some environment specific things which you should be aware of, and I'm going to give you a small example of this U limit. Sometimes it so happens that you might have code. For example, I have this code. What it does is really nothing. It just calls this fun with some parameter which is given on the command line, and that function, it calls itself recursively, right? So the function calls are the so-called activation record. So all of this happens on part of the memory called as stack, and I'm also allocating some array there of some sufficiently good size, 1000 elements, so that I consume some space. Right? So if I try to run this, I compile this ulimit.c and then try to run it with some number, it runs. So it's not, it has not given any error, it has not given any output also. I'm not interested, but importantly, it did not give any error, right? So let me increase that to, let's say, 260, right? And suddenly there is segmentation fault code dumped. This is not a problem with the logic in the program. This happens because of the resource constraint. So the stack size which I'm using here, which is specified using ulimit, that is 1024K, right? And therefore there is some limit, right? So it could be 1024 on your machine or 2048 or some larger value, but more importantly, there is a limit. So it's possible that if I go on increasing the number of recursion levels, it can create problem for me, or if I allocate too much memory on stack, then it can cause this sec fault. It won't be able to allocate this memory. Is there a way I can do anything about it? There is nothing wrong with the program. I mean, I can optimize it, but if this is the problem with execution, I can as well specify a slightly larger limit, let's say 2048. I'm trying to set. I might have to log out and log in here to set the U limit. So let me try that. So U limit minus S 2048. It was 1024 first, and let's see if we had given 260. So let's see first 250 works, then let's see if 260 works. It still worked. It did not give any sec fault. Maybe 300, 2300 is probably too large a value, and so on. And so you can experiment with probably larger values, and it might work for some, it might not work for some, and you can increase it further, right? One of the ways in which it can be done is that you can do U limit minus S unlimited, which means that the stack size is unlimited. Whatever is possible available inside the system, that can be utilized. So that is another way in which it can be done. When it comes to OpenMP, it so happens that we have large number of threads which are assigned to different cores. And we might think that the thread is assigned to a core. If I have 40 cores and 40 threads, then they are going to work exactly on those 40 cores and be done with it. But unfortunately, that doesn't happen in the newest machines. Thread, which is working on a particular core, might migrate to another core, and some other thread might come to this particular core, right? So this thread migration is inherent into the architecture, and you can decide not to allow this migration, right? Sometimes because of this migration, the cache might have to be rebuilt on the new core, or whatever you have populated that might be not useful for the new thread that comes into this core, and so on. So it can cause some performance bottleneck. So one way of doing this, one way of avoiding this migration is by specifying something called as OMP proc bind, right? So you pin a particular thread to a particular core. So it binds the threads to the cores, and that can be specified in OpenMP using this particular environment variable, which can be set using export OMP underscore proc underscore bind equal to true on the command line. Right? If you do that, the time it takes to uh, execute that particular program may change. Again, there is no guarantee. These are just tricks which you might just want to try out. Right? Depending upon your program, it might work for you, it might not work for you. Like I mentioned that there are probably 80 virtual processors on Aqua, each node on Aqua. Similarly, I mean that you could find out using that proc CPU info. Right? There is other information that is available when we are dealing with uh, a machine. It could be your laptop, it could be your lab machine, it could be an Aqua node. But you should be aware that there is a lot of information available, and you should be aware of what kind of architecture it is. Although you don't understand everything, but you should know some of the things. For example, you should know how much memory it takes. I mean, we have on the web page mentioned that it has 192 GB of memory, but who knows, right? Maybe we are lying. You could check it for yourself, right? So, for example, cat proc mem info is going to give you large amount of information about different types of memory. The first line in that output gives you the amount of memory available, and that shows that you have some sort of related to 192 GB of memory available, and then some of that is free, some of that is going into swap, etc. Another output which might be useful, not probably on the Aqua environment, but in your lab system when you have multiple students working on the same machine, where you might not have a queue system, to check if somebody else is running the code, right? So you are performing some experiments, and for a particular problem size, you expect that it should finish, let's say, in 60 seconds. One day you run it and it actually takes 60 seconds. Another day you run it, it runs in 60 seconds. And then the third day you run it, it suddenly takes 100 seconds. Right? So this is not something which is going to be good. And you are not sure why that is happening, but if you want to publish the results, whatever it is the outcome, you might just want to publish. But you should be aware of why that is happening. And sometimes if some other student is running his or her experiments, then such issues might occur. Ideally, one student should be assigned to that particular machine, and only that student should run those commands at any point in time. So the top command can give you information about who all are running what jobs. So especially whichever uh, users are consuming large amount of time. So this is sorted on the CPU time. We can see that there is some genome shell which is consuming some time, and it keeps getting refreshed. Right? So you will come to know if somebody is running this on that particular machine. On Aqua, there is probably not a problem, because the jobs get scheduled on different nodes. Right? Although it is possible that on the same node there might be jobs from multiple users, because depending upon the number of CPUs that they have asked for, it's possible that multiple jobs might be running, and therefore they might share memory, etc. So you might be able to, but if you are using enough number of cores, then unlikely that there will be multiple jobs assigned to the same node at the same time. So you should be aware of this. There is also an interface which we have created, which gives you a queue status, right? So which queue is going to be heavily used or less used, how many jobs it is running, etc. What is the status of those jobs? That is available for Aqua users. So I'm just specifying that here. You should be able to make use of this. So for example, if you click on the small group, it will show you the listing of all the jobs which are running there, and at the bottom it will give you some summary. All right, so let's now talk about OpenMP, MPI, and Cuda. Some very simple tricks. One of the things that you should try is about the schedule. Many times when we parallelize OpenMP, what we do is, okay, there is a for loop. I'm going to add hash pragma OMP parallel for in front of that, and that is going to be sufficient for me, right? So that alone will give you some advantage in most cases, but that might not always work, right? So for example, let me take a simple example. So this is some program related to Jacobi computation, and there is this for loop for which I have added hash pragma MP parallel for, right? And I'm going to compile it using -f OpenMP jacobi.omp.c. And when I time it, let's say I run it for problem size of 512, it takes some amount of time, right? So the sequential time was probably something else. I'm going to probably get a better time by running it by adding that pragma hash omp parallel for. So I do expect that it should give me some benefits. So let's say it does give some benefits, and it's going to finish probably soon. So let's see how much time it's going to take. Okay, so I hope nobody else is running anything on this machine. Okay. So for okay, let it run for some time. But the important part here is that uh, can I change the way the scheduling of work done across work given to different threads changes, right? I think this is taking too long a time. Let me try optimizing it. I think that is something which we definitely studied. So let's see if I can compile it with maybe O3, right? And then when I try to minus, oh great. So this worked much faster. So for 512 size, it took 3760 iterations and it gave some error, but it finished in a few seconds, right? Again, you have to be careful about what time you are taking. One is parallel time, another is addition of sequential times, etc. But we could see that the output was instantaneous. It didn't take really 14 seconds. It was the time taken across different codes. Summed up was probably 14 seconds. Now what I'm going to do is that 0.362 seconds was taken by this. So I'm going to now modify the program. And I'm going to add a different schedule, let's say, some sort of schedule, let's say static or guided. This is just one parameter to uh, this OMP parallel for, and it actually consumed more time. Okay, that's interesting. So without okay, one more thing we could do is to see if without O3 what happens. And okay, last time, if you recall, it had taken a large amount of time, and we actually did a Control C to bring it out of it. I don't know if it is going to take lesser time by adding that schedule. So the point what I want to make here is that by trying these different schedules, you might be able to get different performances. Many times the default schedule. So if you don't specify any schedule, it might use a default, which might not be conducive for the kind of work that you are doing as part of your computation. And like in this case, guided took slightly more time. Maybe we should probably increase the number of the problem size, and that might give you a better difference with respect to the two versions, whether you are using the default schedule or you are using a strided schedule. Okay, so I'm going to close this. It's probably going to take a large amount of time. Okay, so another thing which occurs when you are accessing the array elements, especially when you are writing to array elements, we might have a loop which was a for loop, and therefore I am writing to a of I. When you convert it into a parallel for, that a of I is going to be a of 0, a of 1, a of 2, and that is going to be accessed by different threads. That leads to a problem actually, which doesn't create any correctness issue. You will still get the correct answer, but there is a performance bug that gets created. It's called as false sharing. But I mean, you can read about it later. But the important part here is that if you want to get rid of this, you might want to use a strided access, which means that instead of giving a of 0, a of 1 to consecutive threads, you might give a of 0 to 0 thread, and then a of 16 or a of 32 to thread number 1, and then a of 16 into 2 or 32 into 2 to a of 2 to thread number 2, and so on. So this strided access can help you reduce that false sharing and can improve the performance. This is again related to caching. One important point about OpenMP is that you might want to not parallelize all the for loops in your code, right? So ideally the way to do it is you profile the code, find out how much time is required by different loops, and then parallelize only the ones that are, try to parallelize only the ones which are most time consuming. But there are times when after OpenMP parallelization, the loop might run slower than its sequential counterpart because of the overhead associated with, let's say, thread creation, or there might be synchronization requirement within the threads, etc. So remember that sequentiality is also okay at times. Finally, you are interested in parallelizing the complete application and improving its execution. Okay, let's come to MPI. Many times, whatever job you are doing with MPI can actually be done on a single node also. It's not necessary that you should have MPI processes running on different nodes. So let's say I have 16 MPI processes. In this example, I want 32 MPI process overall. Right? I need not have 32 nodes, right, for my procedure. Maybe I can try doing it in 16 nodes, or maybe 4, or maybe 2. Right? In this case, select equal to 2. That means I'm using 2 nodes, each one having 16 MPI process. But maybe you can try changing it to 1 and see how much time you require. Again, you have to experiment with it, because depending upon the overall communication, this might change. But it's possible that if the communication is actually large across processes, doing it on the same node might turn out to be faster compared to what you have across nodes. One of the other things which I have seen, a little strange, but it does happen, is that some students feel that you can have one MPI run command in the script, right? And then if I want another MPI run, then I need to have another job. No, nothing like that. In the job, you can have arbitrary set of commands. You can have multiple MPI runs in the same script. For example, I have MPI run twice in the same job script. I can actually have heterogeneous processing happening. I can have MPI run, then I can do a Cuda processing, GPU processing. For example, NVCC, I can have multiple A.outs. I can run even a shell script, Python script, multiple times within the same job. As long as you are adhering to the limits that are specified within the PBS options, you are good. Okay. One last slide on Cuda. There are again, like OpenMP and MPI, Cuda also has lots of different kinds of optimizations possible within the code. But some of the simple tricks that you should use is, many times it so happens that we have a large program which we have written either sequentially or using OpenMP or MPI. And then we try to migrate it to Cuda. And it so happens that the code size, the function size is typically much larger. It's a good idea when you are dealing with Cuda to split that processing into multiple small chunks and make that each small chunk as a kernel, as a GPU kernel. Not always it is absolutely possible, but whenever it is possible, it's a good idea to do so. Otherwise, you will have some do-while loop, and then there is another for loop, all inside the same kernel. Due to the way the thread scheduling happens inside Cuda, it's a good idea to try out splitting it into multiple kernels and call these different kernels from the CPU. Another thing that happens is sometimes the kernel becomes very small. As soon as I have a for loop, I'm going to convert it into a kernel. That is the most time consuming. So let me put it and convert it into kernel. That is what we do. But that kernel might be very small because your for loop was very small. And that is not always a good idea, because the thread is going to get, I mean, there are a large number of threads with which you are launching the kernel, and the thread is going to have a very small amount of time to do, small number crunching to do. Instead, it's a good idea to add more work to it, to each thread. How do you add more work to each thread? Instead of doing one I iteration, let it do multiple I iterations. Let's say I equal to 0 as well as I equal to 1. And then thread 2, thread 1, thread number 1 is going to do I equal to 2 and I equal to 3, like that. So let it do more and more work. That usually increases the amount of work that the thread does. And that can improve the execution time. Right? It might actually reduce the number of threads with which you launch the kernel, which has other benefits. But again, these are not foolproof mechanisms. These are more like tricks which you should try out. Right? So that's all from me for now. Hope you find some of these tricks useful. So try these out. Happy computing.